a lot of this comes about, the framework of this in connection to galaxies comes about from an Annual Reviews article that I co-authored with Rob Kennicott. So some of these diagrams come from that. And let's start with the galaxy picture. And so if you look at the star formation properties of galaxies, there's this enormous diversity. If you plot the star formation rate on the x-axis and the surface density of star formation on the y-axis, you see, 4, 5, 6 orders of magnitude variation in both directions. My contribution to this diagram was 1 point. That's the Milky Way. And you can see that it's among the spiral galaxies, which are the sort of normal spiral galaxies or irregular galaxies, not starbursts and so forth. The Milky Way has got a reasonably high star formation rate, but kind of a mediocre surface density of star formation. It's not very centrally condensed. And so that's actually good because it means that there's some star formation going on out in the hinterlands where we live, and we can study it close up. So if you look at that diversity, it collapses if you plot the surface density of star formation versus the surface density of gas, as Kennicott did, for example, in 1998. And this is, of course, one of the famous results for extragalactic star formation. You should note that this is composed of samples of spirals down at low surface density, low star formation rate, and starbursts at the high end. And so it's a composite, really, of those two. In some sense, we shouldn't be surprised that we get rid of a lot of the scatter, because basically we know that gas makes stars, so the more gas you have, the more stars you should make. The interesting result of this was the slope being 1.4 plus or minus 0.15. Now, in the review last year, Rob collected all the data that's accumulated since 1998 and plotted it on the same diagram, did not refit, just plotted the same line with a slope of 1.4, and you can see that it still describes the first order all these galaxies. This particular plot assumes a constant value for the conversion from CO to surface density. And that we'll talk about a little bit later. But these surface densities on the x-axis are basically based on measuring the emission from CO and using a conversion factor to turn that into a surface density. And that has some issues that have to be dealt with.
Just a quick question. So is that molecular surface density then?
This is total gas surface density on this particular plot. Okay. And you notice a couple of things that deviate. In particular, those open blue circles are metal poor galaxies. And probably what's going on there is that the surface density of the molecular gas is being underestimated by using a constant conversion factor. So there are issues that you can see starting to emerge out of this diagram, even though to first order it still does a good job. So the total gas prescription is this equation here with the surface density of gas to the 1.4. And here gas is molecular plus atomic. Now, since I'm among theorists, I have to have a little fun with you. It's of course a great temptation when you see 1.4, it's essentially 1.5. And so naturally you think about the free fall time. So you take the star formation rate should be something like the mass divided by the free fall time, or you can do it in terms of surface density, or you can turn it into volume density, and then you would say that the star formation rate density should go as the gas density of the 1.5, which is basically what the Kennicott-Schmidt law does. And then to be totally unfair, I've seen people say, I put that in my code, I recover the Kennicott-Schmidt relation, and I understand everything. Well, there's a little problem. The star formation rate you get is about 100 times too high. So you have to put in an efficiency factor of about 1%. So this efficiency down here is the efficiency per free fall time. So this looks pretty good. This is work that Mark and Avishai Deckel and Chris McKee did, and showed that if you plot the surface density over the free fall time on the x-axis and the star formation rate surface density on the y-axis, you get a better relation than the Kennicott-Schmidt law. And so this gray band here is, I think, about a factor of 3 in either direction. This is the stuff from nearby galaxies, and they tend to find a flatter relationship if they look at the star formation rate within a galaxy versus distance. So you can see that sort of tilts a little bit differently. But if you put everything together, the starbursts and so forth, this formulation works pretty well. So let's take a closer look. And I'm going to use studies of the star formation rate versus gas in the nearby clouds, the same sample I talked about yesterday. And then we'll talk about studies of star formation rate versus gas in regions forming massive stars. And since I'm supposed to talk about massive star formation, we'll talk about conditions in those regions. A little bit about competing theories of massive star formation. I don't know if you've heard about that. And then what can the observations say about those? And then we'll cycle back to these issues of the star formation laws. So this talk is not kind of nicely, orderly structured like yesterday. It sort of circles around in various ways. So you have to sort of follow this convoluted path. So let's go back to the star formation in the nearby, relatively large 3 to 10 parsec clouds. So the ones with multiple possible star formation sites. If we put together the 2 big surveys of these clouds, and you split them into things that really look like separate clouds, we have about 29 clouds that we can look at. And so we want to look at where stars form, how efficient is the star formation, and how does the star formation rate depend on cloud properties. So here's the Perseus Cloud, which I showed you a little bit yesterday, but now we get a bigger picture. And you can see that the YSOs are plotted in red, and they're highly concentrated. The contours there are contours of surface density, or actually volume density, are inferred from the surface density of the YSOs. So you see the strong concentration, and you furthermore see that the grayscale behind it is a map of the extinction made with all the background stars. The great majority of infrared sources we see in these clouds are actually background stars, and sorting those out requires using all the color information. But with those, you have many objects in which to probe the extinction. And so by smoothing over those, you can get a map of the extinction. You see that the star formation is very highly correlated with regions of high extinction. And the dense cores, as well as the YSOs, are highly clustered. So if I look back at that for a second, the lowest contour, the blue contour there, is 1 solar mass per cubic parsec. And only 9% of the YSOs in the cloud is outside that contour. And the distributed YSOs are more evolved. So the distributed population could have come from more tightly condensed things which have dispersed, because the crossing time is something like the lifetime of a class 2, so they could have moved from their birthplace. The densities of YSOs are high in these clustered regions, but they're still, in this cloud, less than 1/10 of what they are in Orion. So these are still low surface density regions of star formation. The dense cores, that I talked a little bit about yesterday, are even more clustered than the YSO. So the younger the phase you look at, the more clustered they look. Now, one of the questions we'll talk about later is whether cores form stars kind of in isolation. And so if you're forming a cluster, it's made of a whole bunch of cores collapsing to make individual stars, or whether there's a much more dynamic thing in which they're fighting for some general gas. And in these clouds, at least, you can say that the core collisions are not very common. The collision time, the collision time would be about 10 times the lifetime of class 1, for example, in one of the denser regions that we look at. Now, that may not be true when you get to Orion, but in these regions, these things could well evolve in isolation. So just to sort of look at that another way, Eli Bressert plotted for the C2D and Gould Belt and Taurus sources, and also then for Orion, what is the distribution of surface densities of YSOs? And we used to talk about sort of bimodal star formation, distributed mode and clustered mode. And if you look at these distributions of surface densities, you don't see anything that looks bimodal. It's just a broad distribution of possible surface densities. So the way we think about it now is that almost all star formation is clustered. It's just a matter of how clustered. And one of the relevant markers there would be, do you get interaction before you collapse, or do you collapse before you would interact? Okay, and then there's always exceptions to these statements. On the right, you have a piece of Orion. You see highly clustered, dense filaments and so forth. And then on the left, you see one of my favorite sources, B335, which was found over 100 years ago with the revolutionary technology of that time, the photographic plate. And there it's sitting, this dark black spot in the middle of a star field all by itself. And this is the case that I mentioned yesterday where the core, the clump, and the cloud are all the same thing. This is essentially a dense core left all by itself. But that's not the way in which most stars form. Most stars form in clustered environments. So let's address the question of how efficient star formation is. Now, efficient is a word that is abused heavily. So let me try to be clear about the different meanings of it. What I mean by efficiency in these first part here is the mass in stars divided by the mass of the cloud. You can also add the mass of the cloud plus the mass in stars, but you can see since the numbers are small, this is kind of irrelevant. So it's really the mass of stars over the mass of the cloud, basically. And it's the mass of YSOs. So we're taking the efficiency. Remember, we're kind of sensitive to things over the last 2 million years. So this is how efficient is the cloud in forming stars in the last 2 million years. And the first statement is about the dense cores. So in these clouds where we have good data, it's 1 to 4% of the mass is in the dense cores. 2 to 4% of the mass is in stars. Okay, so it's a very small percentage in a 2 million year averaging time. Now, if you look at the star formation rates, you find that the depletion time, if you just ask how long would it take to use up this gas at the star formation rate, it's like 140 million years. That's the average over all of the clouds that I've done recently. And this is almost certainly much larger than the cloud lifetime. We don't have very good ideas what the cloud lifetime is, but I think almost everybody would say that it's certainly less than 140 million years. Now the free fall time, the mean free fall time for this sample of clouds is about 1.5 million years. So the efficiency per free fall turns out to be just about this magic 0.01. On the other hand, if you look at the densest gas, and now I'm talking about take the dense cores, if you just look up at that top couple of lines there, you can see that there's kind of an equal amount of mass in the dense cores as there is in the stars. So once you get the dense cores, the efficiency is reasonably high in that sense. But the core depletion time is still on the order of 1 million years or 2 or 3 million years. And these cores are now dense, so the free fall time's gotten less too. So it's still slow compared to the free fall time. So I will use the term slow to refer to this efficiency per free fall time because there's too many efficiencies floating around. Okay, the other problem you notice is that the scatter is very large. So Charlie Latta plotted the number of YSOs, which is, again, a kind of tracer of the star formation rate because we only trace them over 2 million years, divided by the cloud mass versus the cloud mass. And he gets this enormous spread. And in particular, he points to the fact that Orion and the California Nebula are rather similar in mass, but they have vastly different star formation rates. So Charlie tried looking at the mass versus different surface density thresholds. So what if we just count the mass above some surface density contour? And he found that he got a minimum dispersion for a surface density threshold of about 116 solar masses per square parsec. And then he got rather good correlation between the number of YSOs and the cloud mass. So he proposed that the star formation rate is some constant times the mass of dense gas. Now notice this is linear, not 1.4 or 1.5. Okay, so that was published in the basic result in 2010, and then he wrote a more speculative paper, I'd say, in 2012, suggesting that this was a kind of a universal law. So now we've got 3 different possible predictions here. We've got the Kennicut relation. We could just say, what if that applies, everywhere? We've got the local universal star formation rate, which proposed by Mark and others. And we've got this idea of a threshold density from Charlie Latta. We also found that in a paper with my former student, Amanda Heiderman. We got a little bit higher threshold, but if you take an average, it's about 120 solar masses per square parsec, which corresponds to about 8 magnitudes of visual extinction. So let's see if we can look at these things in the nearby clouds. If really these things apply at the level of clouds, we should be able to test them by looking at this sample of nearby clouds. So first thing we do is look at the star formation rate versus the Kennicutt-Schmidt relation. Now, I point out that the Kennicutt relation, again, is this 1.4. And in nearby galaxies, Beguil and others have found that it's a linear relation and it sort of crosses down there somewhere. And all the local clouds, except for the least active in star formation, are lying well above that relationship. So clearly the extragalactic relationship cannot be propagated down simply to individual nearby clouds. We added some clouds forming more massive stars with the orange boxes there. So, and they lie pretty much similar to the local nearby clouds. So what about the universal local law that Mark proposed? This is for individual clouds, plotting the surface density of gas divided by the free fall time, and then versus that, the surface density of the star formation rate. And of course, the theory with the epsilon free fall of 0.01 kind of gets the mean right. But if you ask whether there's any correlation, you find there's no significant correlation. The correlation coefficient is too small for that size sample to be significant. So we don't see any evidence that the free fall time calculated in this way is very predictive for the star formation rate in these local clouds. Now, one of the things to remember is that this free fall time is calculated based on some mean density of the cloud. And we know that the free fall time goes as 1 over the square root of the density. So you're really calculating the free fall time of some mythical uniform density cloud based on the mean density of a cloud with all sorts of different densities. So that's one of the issues that you have to remember when you compare to a free fall time. And this is the way basically free fall times are usually calculated. Okay, so what about the threshold idea? This is the Charlie Latta idea, and I've just sort of used the threshold value of 8 magnitudes for our local cloud sample, and the star formation rate per amount of dense gas versus the amount of dense gas, and you see that it's reasonably constant around a mean value. The error bar there is kind of what I think the uncertainty is in general, and all the points actually lie kind of within that error bar. So this actually is a pretty good predictor of what's the star formation rate. Now, there's no theory here. This is just kind of what are the observational facts telling us. Now, so the mass of dense gas predicts the star formation rate to within an uncertainty about a factor of 2. What about the total cloud mass? The total cloud mass is bigger, typically only about 40% of the total mass of the cloud is above this threshold. So if you plot the total mass of the cloud and you count the star formation rate per cloud mass, you get a lower mean ratio between those two. But you also get a lot bigger scatter. These points plotted down at -4 are actually clouds with no star formation. So since I don't plot minus infinity, I just plot them there. So they're just clouds with no star formation. And you do see a pretty constant ratio there, but the dispersion is about 4 times bigger. So what about within a cloud? So I was looking at now the free fall time of the whole cloud. Suppose I take my cloud and I do contours of increasing extinction, so higher and higher surface density, and plot the star formation rate calculating just from all the YSOs within those contours. Now this has plenty of issues that we could discuss, and a lot of times you can see all the purple and blue points are essentially upper limits because there's only 1 or 0 YSOs in that contour. And again, the theory kind of gets the mean value right, but what you find now is that the best fit to that data is that it's actually steeper than what you predict with a free fall model. So within the cloud, there's a very steep dependence on the surface density, but there's no real dependence between clouds on the surface density. And part of that's probably because there isn't that big a range in the surface densities of nearby clouds.
So I think in the Perseus Cloud, there is a reason to expect a mean value for the star formation rate. Yes. There is a reason to expect the mean value and not another relation?
Well, this mean value is kind of reflecting, again, this sort of standard efficiency that we tend to see, that on average you get an efficiency per free fall of about 1%. So all clouds that are forming stars tend to have a roughly similar star formation rate per mass of the cloud. There are these ones that are not forming stars. Remember what I said yesterday, those are the ones that have the log normal PDFs. So unless you have that tail on the PDF, you don't form stars. If you do, you wind up somewhere around that point. But the point is that dispersion goes down if you focus on the dense gas. And we remember from our plot of where the YSOs are in Perseus, it's where the extinction is high. So you can kind of get that picture visually. Okay, so the star formation rate seems to increase faster than the prediction of the surface density over free fall time. This is really the idea of the threshold, which has been slightly misunderstood. I think both Latta and Heiderman et al. Suggested the term threshold, but what they meant was this very steep increase. And it's not intended to be a step function. There is star formation occasionally out here at these low surface densities, but it is really much rarer. So it's a steep increase within a cloud that's really implied when we talk about a threshold. Okay, so what are the implications? The Kennicutt relation doesn't apply to individual molecular clouds. These are the molecular clouds near us, so they maybe not be typical of the whole galaxy. One side note is that if you try to take all of the gas, atomic, and molecular within the local square kiloparsec, which is mostly H1 and not active in star formation, and you compare that to the total star formation in this volume, you get something pretty close to the Kennicutt-Schmidt relation. So what that's saying is that relation emerges out of an averaging over many molecular clouds. You have to average over a bigger area. And there's been some nice work lately on just how big an area you have to average over before you get the Kennicutt-Schmidt relation. The free fall time model doesn't describe star formation very well for the local clouds. The best predictor is actually the mass of the dense gas. So let's take a look at that. Let's call that dense gas, the stuff above this threshold, the clump. So remember yesterday we talked about the clump as the birthplace of a cluster. It's where the stars sort of cluster together and form in the individual cores. So the depletion time for that's 36 million years. Still probably longer than the lifetime of the cloud, though closer. And the efficiency per free fall there doubles on average to 0.02, but it's still a lot less than 1. So again, we see that star formation is slow even when we get above this threshold.
So Neal, is that 0.02 using the old time scale for the lifetimes of YSOs or using the new one?
These all use the 2 million years for the class 2. Yeah.
Okay.
So these would all
might come down by factor.
they could all come down by factors of 2 if YSO ages are wrong by factor of 2. Yeah. Good. I'm glad you pointed that out because that's an ongoing issue. But it looks like the structure of the cloud, for example, the column density PDF, is maybe what controls the star formation rate. So that suggests that simulations of these cloud structures are going to be important for understanding the star formation rate. Okay, so now I was supposed to talk about massive stars. So let's take a look at massive stars. The goal would be to study these in a similar way to those in the nearby clouds. But the problem is that the regions forming massive stars are farther away. We have Orion as kind of the only one within 500 parsecs, and if you think about that in the extragalactic context, it's a complete WIMP. It's not really forming stars nearly as copiously as things that we study in other galaxies. So we need a less biased sample. There are galactic plane surveys going on. I'll mention them briefly at the end. This is going to get better. And then we need better resolution. Once we've got a sample, we need Alma and JWST to study the gas and dust conditions, and with JWST, the star formation. So we'd like to get the core mass function. We'd like to see in these regions forming a real cluster of stars, do we have a core mass function that really is the IMF times 3 or whatever. You'd like to resolve the motions and count actual stars. This turns out to be very difficult with existing data. because when you form massive stars, you produce a lot of diffuse infrared emission, and trying to separate the YSOs from that with Spitzer data proved to be extremely difficult. So hoping that JWST might be able to provide the resolution that would allow us to do that. Strangely, you don't need sensitivity, as you need resolution. We also need improved theoretical predictions, and I would encourage you working on this kind of problem to predict more observables. Don't be satisfied just predicting the star formation rate or the IMF. There's lots of observable properties now of clouds, and we should try to meet somewhere in the, before you go all the way to the IMF. Okay, so what do we know now? We have a number of surveys, and these are all biased in various ways. So these unbiased surveys that I mentioned briefly are going to give us a better sample. But right now I can tell you about the existing surveys. So a big survey that our group in Texas had done over many years was based on looking at water masers as signposts. So we're picking out regions where we know there's star formation going on by looking at the water maser, and there's a whole series of papers to study that sample. There is a group led by Henrik Beuther in Heidelberg, who's taken a different sample looking at IRAS infrared sources, followed them up with many different ways. And then there's people who have used these infrared dark clouds, things which show up as dark patches against the infrared emission of the galaxy. So there's a number of different samples. They all found rather similar results. So since I have handy the results from my group, I'm going to show you those, but for the most part, but they're all pretty similar. So if you study one of these regions in molecular lines or dust continuum radiation, you can get a kind of mass, and you divide by the size or the volume, and you get a mean density, or you use excitation analysis of molecules. This particular plot is plotting with excitation analysis of molecules, and I don't know if you can see or not, but the mean of the log of the volume density particles per cubic centimeter is something close to 6. So 10 to the 6th particles per cubic centimeter, and pretty similar over here for the Beuther et al. Sample. So these are quite dense on average, and these are the densities of things that we would call clumps, much denser than the clumps in the local clouds, which is probably good if we're trying to make a massive cluster of stars. It looks like, and this is based on very limited resolution, that they also have density gradients. The nearby, this is really comparing the cores in nearby clouds to the clumps in the high mass star forming regions. So when I put low here, those are clumps, or sorry, cores in nearby clouds, and high is really the clumps in these distant massive regions. But they do seem to have, if you fit them with a power law, you do seem to get a similar kind of relationship. But if you look at the median value of the fiducial density measured at the same distance from the center, you can see that these things are much denser than the local cores. And these are clumps, okay? And the line width is much bigger. So these are really different beasts. So I would call them dense clumps or something like that. And we suspect this is where the massive stars and clusters form. The turbulence is high, that last point about the line width. This is the usual line width size relations based on kind of nearby regions and high mass, meaning intermediate mass really compared to these regions. These regions all lie well above these local relationships. So the line widths are 4 to 5 times larger typically, and you don't really see a line width size relation in these objects. So massive clusters, these are the regions where massive clusters are forming, we're pretty sure. Some of them have already formed pretty extensive amounts of stars. So they form in regions of high turbulence and pressure. Can we see evidence of material falling in or flowing into these regions? Yes, in some. I won't go into the detail of why this kind of profile means infall, but this kind of profile with a stronger blue peak than a red peak can be interpreted as evidence of material flowing in. And a significant fraction, though by no means all, of these kinds of regions show this kind of a blue profile, though some show a red profile, which would suggest expansion. And later work by Fuller found a rather smaller fraction of these with blue profiles. So for the ones where you see it, you would infer a pretty high rate of material moving in. But we don't see this everywhere. And these are, remember, what we would call clumps. They're regions within a much larger cloud. So beware in general, clouds we don't see collapsing in general. The dense clumps, maybe. But the data are so far still rather ambiguous about that. I'll show you some new data recently in a little while. Okay, what about the mass function of these things? This is the cumulative mass function, now determined from the virial masses. And it's incomplete below about 1,000 solar masses. And one of the goals for the future is to try to fill in that lower, lower part of it. The dashed line here is the mass function of CO clumps, so more like larger scale structures, less dense, and that's flatter. In this particular plot, the saltpeter would be minus 1.35, but you really want to compare it to the total masses in OB associations, and that has a slope of about -1, which is pretty close to the slope that you see for these massive dense clumps. So it's very plausible that these are the precursors of OB associations. Now one thing that showed up is that the far infrared luminosity to mass ratio, which is what extragalactic folks often call inefficiency, is 3 to 5 times higher in clumps with H2 regions. So both groups saw that sort of effect. So here's a kind of a summary of the gross properties of these massive clumps. They're obviously massive, dense, and turbulent. Mean masses, a couple thousand, median 1,000 solar masses. This is for the maser sample. They have an overall power law shape in their density profile similar to low mass cores, but about 100 times denser. They're much more turbulent, well above the Larson law. Some of them we have evidence for inward motion. Mass distribution is closer to clusters than the mass distribution of giant molecular clouds in general, and the luminosity to mass increases as the H2 regions form. So let me compare this a little bit to clustered theories of clustered star formation. I don't know, has this been talked about here? The turbulent core versus...
No, they haven't.
Okay, all right. So I will...
He's going to give a talk on it next
okay.
week, but you get to proceed.
All right, I will give a simplified observer's view of what it looks like from our point of view. So the turbulent cores picture presented by McKee and Tan and developed quite a bit by Chris's group is that let's take our picture of formation of individual stars from cores that are presented for the nearby regions, and let's scale it up to these regions and assume that within these dense clumps that we've studied, there are individual turbulent cores which are then collapsing to form individual stars. So the clump has a cluster of these cores. And these cores then have to, the mass function of these cores has to somehow connect to the mass function of stars. A totally different picture developed by Ralph Klesson and followed up by people like Bate and Bennell is that it operates through a process of competitive accretion. You make small seeds in this clump and they move around and compete to sweep up the mass. And then there are hybrid pictures. Phil Meyer's been talking about a picture in which you start with an initial core and then that core collapses, but it continues to feed from the surrounding clump. So this has been one of the big controversies over the last decade, although I think I'll go out on a limb and suggest that maybe the two sides are coming a little closer together. But nonetheless, for observers, this presented a temptation. Let's see if we can prove one of these wrong. So here are the tests, rightly or wrongly, that observers think about to test the turbulent cores. If you're going to form all the massive stars out of individual cores, then you have to find cores that are more massive than the most massive star, because we know the efficiency is not unity. The core mass function must translate to the IMF. That's the idea, I think. We should see infall not only of the whole thing, but onto individual objects. So if we could resolve this flow, we should see that individual cores are falling inward to form stars. And massive stars are fed by massive disks, very parallel to the low mass situation that we can study up close. Now to test all of these things, we need better sensitivity resolution and image quality. It's a very challenging problem, and that's why Alma is the hope for doing this. Okay, what about competitive accretion? In this case, the core mass function should not reflect the IMF, but should center around the genes mass of the clump. The idea is that in these pictures is that the initial genes mass of the clump sets the mass scale, and you make a lot of these little genes mass things, and then they compete. So most of the clump mass would not be in cores, but would be in a more distributed medium. You shouldn't find these very massive cores. And these cores or seeds should be moving around, scouring up the mass. Now, people have also added that you need global collapse. I'm not 100% sure that that's necessary for this picture, but we'll see later that some observers are trying to use that as one of the tests. Okay, so far I'd say the tests are inconclusive. In the nearby clouds, we can resolve cores, but they're not in these massive regions that we would like to study. And what we find is that the cores are moving very slowly, so that's in favor of the turbulent core picture. But there's no really massive cores. If you remember the plot I made of the core mass function, it sort of stopped at maybe 5 or 10 solar masses. So you might say that competitive accretion is favored there, but again, we're not really testing it. Infall in individual cores, unclear. And so we need to study more massive clumps, but they're far away. We need high resolution. We need extremely good image fidelity because it's going to be a messy problem with lots of individual cores in this clump. So what will Alma do for us? So I'm going to present a few things that have come out of the very earliest Alma results, and they purport to support one or the other of these pictures, though I'm not sure they yet do it. So if global collapse is needed for the competitive accretion model, there's a paper, actually there was a press release about this paper recently, so I'll show you what was going on there. They looked at infrared dark clouds, and this particular one published by Nicholas Pareto. And what they find are converging filaments. This is a very common theme that's emerging from all the Herschel data, is that you see essentially filamentary structure, as you also see in your simulations. Now, with Alma, they looked at this, and they saw two sources, some of very high mass in a very small region. Now, to me, I'd say this one might support the turbulent core picture, but that's not how they interpret it. They calculated the virial parameter and said it should be collapsing, and they claimed to see an extended inflow signature along these filaments, and they suggest this would then continuously feed these cores. So this is the slide from their talk at the Alma first results meeting. The two pictures here are actually from simulations showing these flow along these filaments. And then on the right, they have the observations with Alma. And you can see it's a bit messier, but you see from the color coding that there are some velocity gradients, and they might correspond to filaments coming in to feed this region. They calculate the inflow rate of this material at something like 1,500 solar masses per cloud freefall time. So they're continuing to feed this region, and the idea is then that this is consistent in some way with the competitive accretion picture, though I'm not quite sure why that's so true. Okay, so the other way is to look for these massive starless cores. This is the leading problem in the turbulent core picture, is we haven't yet seen these really massive turbulent cores. So Jonathan Tan has been looking for those in infrared dark clouds, and he used Alma using some particular chemical tracers, and he finds cores up to 24 solar masses. So this is good. That's a factor of 2 to 4 better than in the nearby clouds with about the right velocity dispersion. So this is promising, but we need more, and we need to find cores with higher masses if we're going to take the turbulent core picture literally. So those are things that are coming along, and you're going to see a lot more of that with Alma, and you'll see observers trying to decide which of these theories is right, and it may not always be quite the right interpretation. I just thought I'd show you one thing that one of my students did with Alma, and it shows you what you can learn about very young and massive protostars. This is a region in the southern sky It has a very high speed outflow, 160 kilometers per second. It was observed with Alma, and it shows a very compact shell. The nice thing about this is that we can infer a dynamical age of only 800 years. So we're catching something very early in its formation. So explain what this is. The red contours here are radio continuum contours. So there's a region of ionized gas in there. There's a shell of silicon monoxide, which is a tracer of high density shocks. So it looks like this is expanding out. You need about 25 kilometers a second to produce this SIO. And so it looks like there's a fairly high speed shock in addition to a bipolar outflow at much higher speed. So this is a more spherical outflow, or at least circular. And then outside that is a ring of H13CO+, which is presumably being heated before the shock material reaches it. And in fact, if you look at this H13CO+ profile, there's a slight hint of infall. So you can get an image that may or may not be right, that there's material falling in, and then there's also material coming out, and there's a shock between them. So that's just a taste of the kind of things that we'll be able to see now in detail with Alma for very distant regions. Okay, so let's go back to the question of how to measure the star formation rate in these distant regions. And as I said before, you can't count YSOs the way we do in the local regions. They're too distant and confused with the diffuse emission. Maybe JWST will do that for us. So we're forced to use indirect measures. And we've recently gone back and tried to do this looking at free radio emission, which is the most parallel thing to what you do in other galaxies where you look at H alpha. So this is coming from essentially measuring the ionizing photon flux from massive stars. So you're really sensitive to very massive stars, then you have to assume the IMF. The other way you can do in our galaxy is to look at the far infrared luminosity, and that also probes pretty massive stars, and again you have to assume the IMF. So at the moment we have this problem that we have a way of measuring star formation rate in nearby clouds by counting YSOs, and then in the more distant clouds and the ones that are making massive clusters, we have to switch to another method. And so putting us on the same scale is a serious problem. Just to illustrate the point about the IMF, this is a figure from Chomiak and Povich, and the extragalactic star formation rates are all based on this tail of the IMF because they're looking at H alpha or some tracer like that. And if the IMF is different, you could have a problem. Now, the YSO counts in the nearby clouds are measuring masses down in this range. So we're really measuring different things, and you have to hope that the IMF connects them. So another student of mine did a study to try to ask, could we use these extragalactic measures, let's say the total far infrared luminosity, that's what TIR stands for, to measure the star formation rate. And in the nearby clouds, this is the plot of the star formation rate inferred from the extragalactic, the relation extragalactic observers use for the relation between star formation rate and total infrared luminosity over the best measure of the star formation rate, plotted versus the luminosity and the total infrared. So for the orange plots there, which are the local clouds, it doesn't work at all. And when we're plotting, when we say the best star formation rate is the YSO counting. So you can see that it's off by orders of magnitude. There's a sort of a correlation, but it's very noisy. Once you get up to about 10 to the 4.5 in far infrared luminosity, the correlation's not so bad. And so, but up here, well, of course, what we're using now for best is not the star counting, but the free emission. So what we really can say is that the far infrared and the free emission agree, and that's the sample of the massive dense clumps that I was talking about before. Now this is going back and looking at old radio continuum maps to try to get all of the radio continuum and get all of the star formation and doing the same volume for the far infrared luminosity. So this has bumped up the star formation rates in those regions substantially. And Mark and Jonathan Tan showed that you're getting some kind of, when you do these H2 region probes, let's say using free Fourier far infrared, you have to have objects which have been forming stars for some length of time, so your averaging time there is about 5 to 10 million years. So remember, the averaging time locally is about 2 million years. So there are lots of issues with trying to combine these things. So until we got the better resolution, we're kind of stuck with these primitive methods. And so let's look at the star formation rate of the whole clump using either free Fourier far infrared and the mass of dense gas using, for example, the virial mass. Or we'll look at observables, just pure observables, and see how they correlate. So the first thing that we found in studying these large samples is that the luminosity of the HCN 1 to 0 line is a decent measure of the virial mass of the dense gas. So it's a very parallel to using CO to measure the mass of molecular gas. The HCN requires higher densities to excite, so crudely speaking, it measures the mass of the dense gas. And the infrared luminosity correlates pretty well with the emission from dust at long wavelengths, which is measuring the mass, or with dense gas tracers. These are a couple of different things. You get slopes sort of around 1. So the star formation rate, if you can believe that, is more or less correlated with the mass of dense gas with a more or less linear slope. So you remember I had the plot of the nearby clouds showing that the Latta equation worked pretty well. This is if I now add those massive dense clumps where we've recalibrated the star formation rate in red. I'm sorry that the axes are rather dark, but this is the log of the mass of dense gas. This is the log of the star formation rate. These are ones with no star formation, again plotted down here. But you see that they sort of agree now that we've kind of recalibrated the star formation rate in these distant regions. There are still issues, as I emphasized, with combining these, but they do look like they kind of agree. So what about, can we extend this to other galaxies? The galactic massive clumps have some similarities to starburst galaxies, but we can study them in detail. So let's remember that Gao and Solomon pointed out quite a long time ago that if you plot the star formation rate in starburst galaxies versus the luminosity of HCN, which we can kind of translate into the amount of dense molecular gas, you get a linear relationship, not a 1.4 or 1.5 relationship. So the star formation rate is linearly proportional to the amount of dense gas, and argues that the efficiency for the dense gas stays about the same instead of increasing with density. The correlation is somewhat better. There's smaller scatter, lots of caveats about this, but in general, this is another kind of extragalactic relationship. And a few years back, Jingwen Wu and I decided to try to see if we could connect that up with what we know about massive dense regions in our galaxy. So this is the extragalactic sample up there, and this is the group of massive dense clumps I've been talking about. And you see that if you fit above a luminosity of 10 to the 4.5, where we think we're measuring something like star formation rate with plenty of caveats, you get a very similar unity slope, almost the same coefficient. So it suggests that we could connect all of these regions together in some way if we think about the star formation rate per mass of dense gas. Or we could talk about the star formation rate per cloud mass, but with a bigger dispersion. So this is a plot of the within contours for the local clouds, all these stars and diamonds and so forth. These are the previous measures of the star formation rate in the dense gas region, in the massive regions, and we think they're underestimated, so they probably belong up here somewhere. And this green plot is from Dadi's work on starburst galaxies, in which he notes that you need to use a lower version of the CO conversion factor, a lower value, value of the CO conversion factor in starburst regions. And when you do that, of course, the points shift to the left in the plot. And so if he fit those starburst galaxies, which are the black dots, we just put our data on top of that. And it looks like even the dense parts of the local clouds look kind of more like those starbursts. So this is kind of a hint that there are two thresholds going on. This is actually a plot from Beguile's paper. in which they plot now against total mass of gas, hydrogen, atomic and molecular. And you see this transition here, which is a transition from atomic to molecular dominated. And then I think there's not much question about that. And then there's a maybe transition somewhere around 100 to 200, 300 solar masses per square parsec, where you go to a higher star formation rate. So all this depends on what you do with the conversion from CO observations to surface density. So it's all still very questionable, but there's some very interesting hints. So this leads to some speculation that there may be these two transitions, one around 10 solar masses per square parsec and one maybe around 120 or thereabouts. Probably very uncertain. Almost certainly this threshold depends on other things like the external radiation field, the Mach number, so forth. So we really want to put massive star formation in a galactic context. And there's a lot of work that's gone on over the last decade that's coming to fruition now. Surveys of the northern and southern galactic planes at millimeter wavelengths, finding thousands of dense clumps that we will then be able to study in a more systematic way, a less biased way. And Herschel has mapped the galaxy in the HiGal project. And once all that gets put together, we'll have a much clearer picture of what our galaxy looks like in this more or less clump level gas. The infrared dark clouds have proved to be very useful. To make all this work, you need to know how far away these things are, and this is a serious problem. So there are people working on new models of the galaxy using the VLBA to get distances to masers, and therefore putting star-forming regions into the correct model of the galaxy. So once we do that, we'll have a better mass function for clumps and better measures of the star formation rates. And we can be able to link all this better to extragalactic star formation. So this is a summary. I had a couple of extra slides, which I think I have time for. So let me come back to the summary and just show you a region that I think is particularly interesting from this point of view. In the central molecular zone of the galaxy, there are some very massive, dense clumps. One of them is called the brick. And there's some observations, again, early stage Alma observations of this region. But I want to set up, before I show you those, I want to set up what's going on. So let me zip to the next slide. This is from Steve Longmore, who's been looking at this situation carefully. The gas in these clumps in the inner part of the galaxy is very dense. It should all be well above these local thresholds. And yet, this particular region, this brick, is not forming stars quickly. So if you look at the different relationships here, here's Orion, for example. And this region over here, this is the brick. It's much more massive and it's dense, but its star formation rate, it's really kind of a limit, is actually quite low compared to what you would expect. There's enough dense gas there, as he puts it, to produce like 1,000 Orions, and yet the star formation rate is comparable to a single Orion. So this is a region that provides a very good test of star formation theories. So let me talk about the Alma data a little bit here. The resolution is now getting down to the size of cores, more or less. They see a lot of continuum structures. Don't see that. I'm not going to show you that because we didn't see it. But there are filaments, arcs, and things that they might call cores, and they've sort of identified 50 cores with masses up to 900 solar masses. So if right, this would be very interesting for the turbulent core picture. But they are not willing to talk about a core mass function yet. At least they weren't as the last I talked to them. There are a lot of SIO emitting structures, and remember I said that there's a tracer of shocks. And so this is a very highly turbulent region as well. So let me show you the data now. These are maps in the SIO and two other molecules of this so-called brick. And you can see there's a lot of information there. It hasn't been fully digested yet. But this is a good test case when we understand the structure, internal structure of this thing, and compare that to predictions of models that are running with much higher turbulent velocities and higher densities, some explanation of why the star formation rate is so low here. And Paul and Simon have some suggestions about this, which I think you mentioned the other day. So this kind of says that we will be getting some better observations of this region. Okay, so let me go back to my summary, and I'll just stop there and see if you have questions.
All right. People clearly either understood everything or are very hungry.
Yeah, or come and have lunch with me and ask me anything you like. So.
All right, that's great.